Okay, so my name is Fabrice Hernandez, working at Mercator Océan. And I'm here because I'm in charge. I've been asked for years to be chairing or co-chairing one of the task team in GoDaddy, and then in GoDaddy OceanView, called the Intercomparison Validation Task Team. And I'm also coordinating in the Copernicus Marine Service the activities concerning validation and verification among the different centers that have been presented by Marie yesterday. So from that, I have a series of ideas about what we are doing and what we should do in terms of validation, verification in our operational system, and how to measure the performance of these systems. And I want not to cover everything, but to highlight some points. And also, I'm, I would say, happy to present this lecture, I would say, at the end of this 2 weeks work for you, because you have seen, and you have just seen with Sylvain, that we are all using these concepts of metrics, performances, measuring the errors in our systems for different purposes. The main difference from the lab and the academic world and the operational geography are in the fact that we have to offer a service, and we are now focusing on these aspects. So my outline, giving you back some concepts and priorities, and obviously give you lots of examples from what we have done in the framework of GoDaddy, then GoDaddy OceanView, and also the Copernicus Marine Service. I'd like to address some issues about how we need to communicate with users, or at least what our experience at the moment, and then give you some ideas about the new metrics and challenges we are facing. As I said, there are different groups at the international level that are working on these aspects. I want to here mention the intercomparison validation task team in GoDaddy OceanView, with lots of participants, and the main participant that provide lots of nice interaction and results. And also we have a big group, the Project Quality Working Group in Europe, working on the Copernicus Marine Service, coordinated by these people at Mercator. And again, this group is quite active and providing lots of inputs for what I'm going to say. And I'd like also to mention that GoDaddy OceanView have this intercomparison evaluation task team where we are tackling part of these different issues concerning validating our systems. But there are other task teams that also deals with how to measure the performance of what they are doing. So here, just to let you know, we have an active group in Europe. This is a picture from the second meeting we had from this Copernicus Marine Service group, working on how we look at the performance of our real-time system, but also the reanalysis. And at the international level, we have many people. And here you have Greg Smith, my co-chair in GoDaddy OceanView, and at his side, Katia Fennell, one of the co-chair of the marine ecosystem and the biochemistry task team that also deals with assessment issues. I want to mention also in GoDaddy the coastal and shelf seas task team that also works a lot on how to evaluate the regional and coastal models, and John gave you some good inputs about that. So you can see that in GoDaddy we are doing lots of things concerning how to evaluate our systems. I'd like to start by some concepts and the priorities we identified. Just back to early days, This is just a figure of one of the first intercomparison published with different models on the same area, trying to assess their performance because they have different kind of vertical discretization. And this was published, and in this case, they were using one metric, the meridional transport, heat transport. At that time, people were looking at ways to verify and evaluate their system for different reasons. First, to use their model to understand and describe the ocean, obviously. Also, they were performing some difference with data and so on in order to calibrate their system and their internal mechanism of the models that was presented by Julien, Eric, and so on. They were validating to evaluate then the error of the system before interpreting their results in terms of ocean dynamics. And like here, trying to compare their different ideas with these models in order to progress with others. Then we move to, in the 90s, to the idea that we could use all this activity concerning models, observation, and so on to start to describe the ocean and trying to provide an integrated view of this ocean. First, using satellite and in situ, so I don't come back on that aspect. You have different lectures showing how rich is now the satellite constellation that provides a lot of surface measurement, and how interesting is becoming the in situ observing system with all these new sensors. And from that, you could create observed products that could be provided to a wider community of users. And obviously, you were facing, when you did that in terms of evaluating the quality of these products, of the observation errors, the observation representativity in terms of distribution and sparseness. And obviously, if you were using the data by merging them to create some consolidated view of the ocean description with the limits of the tools you were using to do so, estimation and mapping error, for instance. And you were limited also in the way you were evaluating these things because the few observations you had could not provide a complete view of the ocean processes. Then we start to introduce models in the game. And the models also you wanted, as we saw these 2 weeks, to validate them. And you are facing, from these model components articulation, lots of errors you wanted to understand and maybe control. Obviously, the forcing you put in your model and the runoff, the shape of the bathymetry may put some errors, initialization, subgrid parameterization, numerical errors, nesting errors, and obviously the model choice that brings a given representation of this ocean. And to validate so, you wanted to use also the data available or other ways, but we were always facing one limitation. We have not the capability to monitor every single variable and every single parameter in this model framework. Then we decided, because from the atmospheric community things were a little bit mature, to introduce data assimilation in the 90s and to start to build these systems that incorporate observation plus model through data assimilation to provide at least analysis. And this analysis, you wanted to, again, evaluate them, considering also a series of errors like the representativity, the assimilation method itself, and many things that were presented already. And one of the limitations, again, in evaluating this new description of the ocean was the fact that, obviously, you were trying to use every data you could to assimilate into your system to get a better solution. And obviously, once you have used these data are not independent for the evaluation. So this is also a limitation. Finally, things start to be mature, and you decide to run that operationally and to do some forecasts. and you want to evaluate your forecast. Forecast also have some errors you want to control. So in terms of the performance of the system and the forecast skill, again, we had already the atmospheric community and the weather and climate forecast that have been working a lot, pioneering lots of things. So we had published many good ideas to use in terms of evaluating this forecast. And again, limitation in terms of evaluation. Forecasts are usually for the real time to provide services for users for prediction. And in real time, we are less observation than ever for all the reasons you have been told these past 2 weeks. The time you need to get the data, or the data are not good, or data are at depth and you will recover the data in wire time and so on. So one way to measure the performance of the systems is maybe to work on delay mode validation, so waiting a few weeks to get more data for validating, for instance, or doing some retrospective experiment in order to measure the performance per se at your system. So in practice, in operational oceanography, your objectives are to evaluate and monitor the performance of your operational system and measuring the impact of the observing system, the model's errors, and the data simulation efficiency. Then you have products to offer to users, so you want to evaluate the accuracy of this product. And you have different kind of product. You may have product, this was shown by Marie about the Copernicus Marine Service, derived purely from observation. You have products so derived from the complex observe plus data simulation and model that provides forecast, and you have the reanalysis. And the last thing you want to do is to measure the strengths and weaknesses of your operated system for further improvements. So this is called, in our jargon now, internal metrics, and this is internal science-driven, obviously. All these things are the things dedicated to operational oceanography, but you could imagine to do in your lab, even if you're not in operational framework. And there is something quite important to consider in operational oceanography. We have a main objective, and the main objective is to provide robust and reliable products for a useful and cost-effective service. And that brings us to another issue in terms of objectives, is to assess product reliability considering users' needs. And this is new when you leave your lab, because you're not accustomed to that, is now you need to think about all you do in terms of user-driven expectation. But what I'm saying is just the concept. You have seen that just Sylvain was showing that he has users, he has ship at sea that want to know where is the ice. So these kind of things are quite common and understandable. So we are facing some challenges and user expectation. The same thing in practice that are facing the weather community and the climate forecast community for years in terms of assessment. So what we need to do to move from science-driven to user-driven views, and we have challenges in understanding the user request. What do we need to evaluate? And we have also challenges in the fact that our systems, because we are working hard, are more and more complex in order to offer better service. So you have seen these 2 weeks that we have now systems that are coupling atmospheric, wave, ice, biogeochemistry, maybe river systems and so on, systems that are nested into other systems in order to have different kind of scales. You have diversity of products. You have seen the blue, the green, and the white ocean just this morning. And we have different objectives in terms of serving different communities, climate, seasonal, short-term prediction, open ocean, coastal, and so on. So these are all the things we are facing in terms of service we have to offer, and we have to adapt our evaluation to all this new branch of things. And also, which is also new for us, leaving our lab to the real world, if we have to cope with many applications and we have to cope with decision maker in the real life, in the real society. So it means that we have challenges in communicating our product accuracy and reliability. So now a few words about what we are doing since when we started to think about these things in GoDaddy. So Christian Le Provost started to work with a group of people about what should be the good principles and metrics, also referring to existing work, for instance, by Murphy in the atmospheric verification community. We define a series of principles. Consistency, we want to assess our system on a basic way in order to ensure that they are consistent compared to the current knowledge of the ocean circulation and dynamics, typically with climatology. Then the second step is to measure the quality or the accuracy of the INCAS or analysis and compare usually to the sea truth and preferably with independent information, not assimilated. And then, as I said, we are giving some predictions. So we have to measure the performance of the forecast, okay, accuracy of the forecast. And so big question like, do we perform better than the persistency, better than the climatology, and so on. And as I said, we have in front of us some users. So we also define another principle, which is the benefit. What is the benefit for users in our practices? So in this framework, for instance, in the Marine Service, as I said, we have a product quality working group that works a lot. And we decide also to have a strategy written in these documents recently, where we define, obviously, what we call all the internal metrics. I would say the as usual way to work in assessing all these things. And you want to satisfy the initial requirements. Typically, you design a model, an operational model without tides. If you compare to a tide gauge, you filter the tides, and you want to measure all the scales in your system compared to the scales observed without what the system is not designed for. So this is initial requirements, and you need also to look at the interest for users. So external metrics. In the same idea, from the same tide gauge, you want to give to the users the information about my system is that way. I don't put the tides into my system. So the departure from the real world compared to this tide gauge is that. So this is an external metrics. And the way we are working in the Marine Service is we want to have our activity in terms of validating and verifying the things that are close to state of the art. So we regularly update our framework with what is published. We want also, Marie showed you that there are lots of production centers. So we want to have this framework of verification and validation homogeneous among us and applied similarly to all the bunch of products we are providing in the Marine Service. And obviously, we want to monitor the continuous improvement of our system since we start all together in Europe with the MyOcean project. So, few words about the progress we have made since the beginning of GoDaddy, for instance. Just to mention that since we've been working in GoDaddy, we have made lots of progresses in these ideas of evaluation of operational oceanography, and it allows us to implement lots of things in our systems. So obviously, we wanted at the beginning to work all together for a series of things, and we designed an anti-comparison framework inside of GoDaddy with different global ocean actors. We started by designing metrics, implement and compute that metrics, defining a framework to work all together, which means exchange data, define standards, etc., etc. Then perform the assessment of our systems and intercompare, and then publish results. These two things are really demanding. When you run big systems, you want to, and you have your systems produced in output in your native grid, which is a grid, your grid. And you decide to work with the other, it means that you are going to maybe either move all your output into the grid of the other, or adopt a common grid, which is that you have twice the storage to define, for instance. And then you have to exchange that, and then you have to work with the others. So working all together and intercomparing is demanding. So the few metrics we designed are still there in operation. For instance, the class one where what we call the gridded view of the intercomparison. All these metrics are based on model field interpolated into predefined grids, and we define areas, and we are going to compare from the different system the different variables. The second aspect was to refine in precise areas. Either we had observation there on fixed location like moorings, or either we wanted to look at a specific sections. So these are called the class 2 and class 3 sections where we can compute integrated quantities. So these are, for instance, in the beginning of GODAE, all the points we identified in sections that were of importance and interest. And then we have the class 4 metrics. I'll come back on that. That allows you to measure the performance of the system. So this is grid 1, for instance, comparison between Mercator and early days of Topaz, looking at the sea ice concentration, measuring, you see differences compared to what existed. These are satellite observed values on the Arctic and Antarctic. Then you had this class 3 looking specifically at, or class 2 looking specifically at a section here. So we had on that section, we had only the climatology, so refer to the climatology based on WOS section, for instance, and comparing our systems here to this climatology. And also, for instance, here, we use that in Mercator also to measure the improvement from a first system to a second system. Another example here, the well-known cable data for the transport at the Florida Strait. So again, we had this data, what we call class 3 information, integrated information, and we could compare several systems and trying to understand the limitation of each of these systems to real observed information in terms of transport at the Florida Strait. Then this exercise was successful, and we had a symposium where we demonstrated that GODAE intercomparison activity were a success, but the most important that we started to share expertise and ways to work, and we show that we could work all together to assess our system. So all these systems were involved in GODAE. These systems had different models configuration, different forcing, and different assimilation scheme, and ways to assimilate part of the global observing system. An example again on the so-called class 1 assessment, Mercator and foam, SST, surface, compared to here an observed product, Ostia, and also a regional, not only global, but also the Canadian regional system at that time. So we had possibilities to compare the system to what was observed. Just one point here, what I want to highlight at that time, if you look carefully at the scales, you will see that at that time, the SST product that we refer to, that was our Ocean Truth, offered less shorter scale that the different SST estimate for our system. So we had already facing another thing was the limitation of the representativity of the reference information we were using. And in this case also, when we have this kind of map, usually this is from objective analysis or some mapping technique, and we wanted to use at that time the analysis error associated, and obviously there was a problem here with this analysis error. So you see that when you start to work on things, you progress because you have lots of things to solve and to share with other groups. Another example of this assessment here, always SST, looking carefully at the tropical Atlantic on two classical boxes, and we could a long time. These are the time series of differences, not differences, direct comparison to the Ostia product, and we could evidence departure and interesting things among our systems. Same thing, looking at another aspect of our system, which is the turbulence through the eddy kinetic energy, the turbulence contained in our systems. Topaz foam, and again the Canadian regional system. And again we saw, for instance, that at that time the Mercator system and the ICOM were 1/12 degree resolution and the others were 1/4. Obviously, there were more turbulence, and we could characterize and quantify that things working all together. Now, class 4 metrics in order to infer performances of the forecast capability of our systems. An example here, we have a series of temperature and salinity profile from Argo, moorings, and so on, XBT sections. We can use that, projecting our model into the exact values given by the observed things. So projecting being not in the model framework, but into the observed space. And we can compare, and these are, for instance, comparison differences at different layers. So this is a mean of from 0 to 50 meters, from 200 to 700 meters, and so on. And so you can measure the discrepancies between your systems and the observed value. And you can do that for the Ncast. You can do that for the best estimate. You can do that for the forecast, any forecast, because I measure something today, and I can wait a little bit, and if I compare to the forecast I made 2 days earlier for that day, I can do my comparison. So this is what we are doing, defining boxes in order to perform statistics by compiling all this information all together. And this is the class 4 approaches, where you want what? You have the truth that you don't know. Then you have the observed values of that truth. And then you have your system that runs. So your system is running, and you assimilate. So you improve your system towards the observed value. And you have the climatology, and you have what we call the persistence, which means that from time t to t+1, you just consider that what would be the added value of my system that are dynamically changing the full dynamics compared to a view where I'm not changing anything and saying the weather of today is the same than yesterday. This is persistence. And we are trying to measure these different estimates compared to the observed value and quantify that. And this is what we do in terms of performance and class 4. So examples, recent examples. So in Copernicus Marine Service, we have a regional system that have their own validation page. So this is, for instance, for the Arctic system. So they look, in this case, at the surface temperature. So this is the number of buoys for a given day in the window apart. And they measure the base estimate, the forecast, and the persistence. So you see that they try to check if they beat the persistence or not. This is the bias. This is a view directly with all these buoys with the departure, and this is the RMS errors. So you can do these kind of things, and you see that, for instance, in time, the forecast beats the persistence. So the guys in the Arctic can be quite happy about the way that their systems and their model provides better information for the future than just saying today tomorrow would be like today, for instance. All these things were in the frame of GODAE also presented through dedicated assessment and intercomparison. So in 2013, we started a new intercomparison framework with different partners around the world, and we define new metric. This has been published, and for instance, this is a new metrics. This kind of target metrics allows to here you have all these systems, these 5 systems, and you can measure days after days the performance of the system for different variables, so salinity, temperature, sea level anomaly, and SST, and you measure how the systems are behaving using all your class 4 metrics. So this is published, so I go fast. The benefit of working all together, so we started by having in this new intercomparison this system working all together, but now we have the other regional system that are joining us, so we're quite happy to start to work with them. Another way to show this kind of assessment, for instance, so looking in time of the correlation of the different system. In gray here, this is the number of observations. So we also monitor the observed values that enter into our evaluation system, and this is also a way to witness how the global observing system is at present. Another just illustration of a new forecast skill, this kind of bar chart for correlation, give you the quantile 95 countries, so to give you an idea also of the spread on your statistics for a given metric. And this is also new in the way this is Charlie Renier, colleague at Mercator, that provides that. We are on this every small boxes looking at which system offers the better results. So it's not a competition, just to show where a given system offers better performance than the others. And if we zoom in this area, we had, for instance, also the Australian that were interested in particular in this area, and they are also constructing this kind of a figure where every system is monitored. This is lead time, this is forecast for SST and sea level anomaly, and we can check how our system are behaving. And for instance, there is no competition, but we identify that, for instance, the UK Met Office system is really good at the beginning, and then more or less is on, I would say, the performance of the others. And obviously here they do special things, or they do overfitting that brings their analysis closer to what is observed. So this is just an example of the conclusions we have by doing so. And recently, this is a community success. We had the global system from the NMMFC, the Chinese institute, that joined us, and using the same framework and metrics, working with us, also measuring the performance of his system. So you see that this is an ongoing effort, and where we have all interesting. This is a winning activity where we all have interest to work on that. So for the past 2 years with Greg Smith, we have a GODAE meeting every year. Now we try to provide this kind of evaluation for all our systems. So this is some kind of monitoring where we see, so as I said, in gray, the evolution of the observed values we use and the performance of the system. So you see, for instance, big changes here. And obviously these changes were identified as change in the version and upgrade of that system. In this case, this is the Australian system. We are also looking at different things. For instance, we have these spikes, and what happened here, it's just because our colleagues here didn't use the same quality control when using the observed value than us, which means that they have this kind of spike. So we mentioned to them that evaluation tool needed to be changed. And we have lots of things we are looking at. For instance, here again, the Canadian system that seems to be really depending on this variability seems to be associated with the fact that we have more data here, so a sensibility to this observation at that time. We also saw that there were sometimes really correlated changes like here or here, so we need to look carefully about these things. This is a zoom. You see that all the system the performance was at that level, and suddenly all the system are bad performances here. So, and all correlated. So we need to understand what is happening. So this is what I'm saying here. And looking at depths, comparing, so class 4 is for different observed value, but in particular T and S at depths. So comparing our different systems, RMS again, and biases statistically average over different areas for temperature salinity. And we see, for instance, some spikes here. Obviously, again, the quality control technique was not the same in our different systems, so we are let the others about that kind of things. And we can look at different ranges at depths, looking at things and measuring things. And for instance, obviously, here at depths below 1,000 meters, we discover that all our systems, all of them, are the performance that are diminishing. So this is new. We want to understand why, and one possibility is that because we are more salinity profile that are creating more variability at depths, and maybe we have to look carefully at these kind of things. What next? What can we do with all these things comparing our model value at the exact point of the observed value? Well, we can go further and create metrics much more either process-oriented or user-oriented. For instance, using the TS comparison, direct comparison, to build up on TS diagram in order to look at the water masses provided by the different systems. So, for instance, here, this is in red the climatology, and then the in situ values and the model values. So you see big discrepancies in this diagram, showing that the Mercator systems for that type of water have a problem, and we need to find a way to correct that. Another new metrics we could do is not just only compare a long track satellite altimetry between model value and observed satellite data, but we can do, as was mentioned by Rosemary and other things like spectrum, so spectrum in this area, in order to qualify the scales. For instance, Jinshan Shu in Canada did that, and showing that obviously the 1/12 degree system for Mercator is closer to what is observed in terms of scale by the altimeter for the spectrum than the 1/4 system. So it's a way to quantify also days after days the performance of our system. Now going to sea ice. We are doing lots of things also at the GODAI level and at the Marine Service level. So for instance, comparing MSR2 on daily basis with the sea ice concentration for different systems. So this is just an example with Mercator provided by Charlie Régnier, and the different colors concerns the best estimate and then the forecast and the persistence. And the idea is to check if on time if we are beating the persistence or not with different things like the RMS differences, and we do that because we all providing our data to the same server, the US GODAI server. Everyone can download the data and do some comparison. So Charlie in Mercator did that using the Canadian results and the UK Met results compared to the Mercator results. These two systems are at that time were assimilating sea ice concentration. Mercator was not. So you see that the errors in Mercator are more important in winter than other systems. And other system, and because we are not assimilating, this is the model alone. So whatever you do in terms of comparing today and tomorrow, we have a few differences in the score, while you see the big differences in that system where obviously forecast and persistence have scores that change a long time. Another approach, which are more sophisticated metrics in terms of contingency tables. So now we are again in terms of user or process-oriented metrics. In this case, for every point, you are going to check if there is or not a given event, a given occurrence. In this case, data or water, ice or water, and you create this kind of maps with heat of ice and heat of water. So success, miss, and then false alarm. And you create this kind of metrics, and then you can build. This is Greg Smith that did that. You can build this kind of metrics with the different quantities refer here, and looking at the performances of the system. So for the northern, for the Arctic, for instance, with again the Canadian and the Mercator system that was not assimilating ice, so you see bad performances for the Mercator system. And then last year the UK Met system entered the game, and these are the two Canadian and UK Met system, and again the Mercator system that do not have assimilation. So we can quantify the different performance of our system this way. For the future, new metrics. Charlie Régnier was trying to have something more fancy, looking, for instance, at sea ice age alerts, warning us when we are far from reality, I would say. A little bit about surface velocity. You have seen with many examples that at the surface, surface is important because we have lots of application in terms of oceanography, search and rescue, oil spill. Lots of industry are near the surface and near the coast. So we have to care particularly to the surface dynamics. So, for instance, what we plan to do is to use the global drifter program with all these drifters drugged at 15 meters, and in order to try to do some assessment. So this is again provided by Marie and Charlie. This is done at Mercator alone, and we want to have the other group in Godae doing that kind of things. So along the here, this is the drifter trajectory, and this is just the velocities at the drifter trajectory for for Mercator and for the observed value. And what you can do is point by point to measure the differences. So this is, for instance, the difference in the zonal velocity. So comparing the zonal velocity of the model and a long track of the drifter. And you can also measure differences in terms of angle, for instance, build statistics. So you can sum that into a box and do some statistics, PDF differences, and so on and so on. Or you can do something more sophisticated that ask you to do more effort in terms of implementation of tools, which is Lagrangian metrics. So the idea is here, for instance, to have the trajectory of your drifter, and every day to start from the real trajectory of the drifter and to simulate with your forecast value of your surface velocity from the model, to simulate a trajectory and to compare after one day the departure between the real observed position of the drifter and what we have predicted after one day, after 2 days, after 3 days. And you do that every day. So you build up that kind of statistics of departure after one day and so on. So this is also something we try to do at Mercator, and we want the others to do, to learn about for 1 day departure of, so this is mean Lagrangian distances, and this infers you where the systems spread too much the possible particles or not. And this is for 3 days, I think. So you can build things like this and look at specific area and measure in where area the mixing properties of your system are adequate or not compared to drifters. Few words about ensemble approach in the frame of Godae. We had also the idea to share every day our native grids, and this came after one of the accident, the Air France Rio crash. We thought that was a good idea to offer to other Godae operational system or data instantaneously in order to allow them to, if they need, to grab all our data and to do ensemble forecast using the different data. And we've decided to concentrate on surface parameters and to provide that on our servers in order to allow everyone to do something. Few have been done, but Todd Spindler from NOAA has done lots of things with this new exercise. This idea was to measure using these things and comparing to observed value from the class 4 the performance of the ensemble mean. And so use the different system, used also France data for doing lots of things. And in practice, what he did is to get the data and compute different kind of ensemble mean through different kind of cluster techniques with weight and so on. And obviously, this is successful. So this is a Taylor diagram for just showing the sea surface salinity, and you know how sea surface salinity is erroneous in your system due to all you know now about forcing, precipitation, and so on. So obviously, so these are individual performance of the system, and these are the different kind of mean he computed with a cluster mean, weighted mean, and simple mean. And all the time, in every area, the ensemble are beating in terms of performance the single models. Same thing for another really sensible parameter, surface zonal velocity. Again, all the time, the ensemble mean, whatever are the way they are computed, are beating the individual systems. So this is also really interesting to take into account into our ways to evaluate our systems. Another example of what Todd did, comparing, so I think this is S16 Gulfstream, and comparing the different system, individual system, and the ensemble mean. Obviously, again, you have a better representation of the Gulfstream pattern when you average the different systems, which means that back to Julien Sommer, le Sommer conclusion, we have a lot of learn about the natural variability from our system compared to what the system are really, I would say, reliable in terms of patterns. Again, also at depth, again the ensemble beats the other systems. Now, few words about informing users on accuracy of our systems. We need to take into account something new for us. We did lots of user forum and meeting with users in Europe this past year with MyOcean and now with the Copernicus Marine Service. And surprisingly, users first need, in terms of service, timeliness and regular dissemination. They tell us that the first thing we want is every day the product on the servers first, even if the products are erroneous, which means that, of course, they want accuracy, which means that second, we need to offer them a good evaluation of the quality of our systems. And then what they request is anything. When you look at the inquiries, they are going, depending on where they come from, they want more resolution, more physical content, more things. So, but the two main things are these things. So this was quite new for us. Ways to inform users. You have many ways to inform users about the quality of your product on the everyday basis. You can publish results and ask them to read your nice publication in Nature. Okay. You can make direct meetings with users. You can alert them regularly with a time-immobile communication based on many medias, emails, alerts, warning system, website, maybe Twitter, and maybe other ways to inform them on the quality of our system on a daily basis. What are the kind of information we need or we can provide? Performance and accuracy level. From all the assessment we have performing as usual, so I would say the academic classical way. We need also to think in terms of process-oriented results against the real ocean. So this is the external metrics I mentioned. And maybe, but this is much more demanding and this needs to have a close link with them, work on user-oriented metrics. For instance, you have a user that uses your system, search and rescue, for instance. He has a search and rescue application. So maybe you need to look carefully at Lagrangian properties and so on to better inform him about the quality of our system. Just an example from our colleagues in the Mediterranean Sea in the Marine Service Framework, what they did in terms of creating the framework for validation. They identified different parameters, different data, created different metrics following the class 1, class 2, class 4 approach, and different areas of interest, and they build their results with estimated accuracy numbers. These are published into documentation like we call the QUID in the Marine Service, where we provide an executive summary with these accuracy numbers and description and so on. These quids are available if you go on the site, on the catalog, when you get more info and documentation. So there are documents for every product. And in parallel, what we did is to provide an evolving information about the quality of the different systems in the Marine Service through a website where we use class 4 metrics, comparison to observation, to monitor quarter after quarter the performance of our system for the different systems, different parameters, and so on. And what we are going to do now is to incorporate also specific regional websites from the different operation center. For instance, again, the Mediterranean Sea, where they look at different performances much more localized into their area. And for instance, here since 2013, the performance of their system that is, you see, growing with time. Another example here, against fixed mooring, so comparing at mooring location the velocities. And something quite interesting now, we can, and this is in the framework of comparing in the nested strategy regional system and global system, where you want to measure the added value of a local system compared to the father system. And you can do this kind of metrics. So this is done by our colleagues in Spain. where they also compared the reanalysis, for instance, here in this fixed position in the Canary Island, looking specifically at this kind of chart about the velocity field, and also looking carefully at Lagrangian aspect of that with this kind of progressive vectors approach. Another comparison for the global here reanalysis, where they compare global reanalysis in the EB area. So again, Irish, Biscay, Iberian Shelf system, where we see that the local reanalysis is better than the global reanalysis for many parameters. To inform users, we may account now into something new. This was a slide provided by Giovanni Copini in the MEDC that tries to develop new application to reach users. So they have a new system, and this system is based on web portal, tablets, and iPad. So the challenge for us is, how do we inform you here in this room in the future? How do we inform users using this media? Few words about ensemble performance. So you see that ensemble performance allows us to monitor many things. In particular, if we consider that we have uncorrected errors in our systems, this is also a way to exchange and bring community effort through intercomparison. And obviously, this is done in climate and weather forecast community, so this is interesting to follow. So what we are doing with our new approaches is to look at the spread of different systems, compute the ensemble mean, and maybe use this ensemble mean as something for users. And we identify outliers from different individual systems compared to the ensemble. So an example here, new, we are going to implement in the marine service. The Northwest Shelf system compared to EB on the overlapping area, for instance here against so this is SST, and this is chlorophyll. So you see, for instance, in chlorophyll that our system need to be improved in many ways, and we try to have correlation metrics and so on. Another new things, this is again looking at coastal versus regional and global. So this is a comparison to HF radar, where we can infer lots of things at very coastal scales and understand what are the performances of our different systems. Ensemble approach are used in the Baltic Sea, in the Copernicus Marine Service Framework, in the Northwest Shelf area also, and also at the global scale. Recently, we released a series of new reanalysis, global reanalysis from 4 systems, and what Marie and others did in Mercator is to do the ensemble mean and measure the performance on the ensemble mean in black compared to in red compared to no. So this is climatology. This is ensemble mean, and this is here you have a nice explanation about first the observed world, second the spread of these different reanalyses over time, 92 to 2016, and also how this ensemble mean beats or not the different individual systems. So we have a lot of learn from this ensemble approach. Last thing about ensemble, in the Baltic, they don't have ways in the middle of the Baltic Sea to measure transport and surface current surface properties. So they decided to define transport sections and to compare the values at the transport section without data, and also to infer the ways they are spreading in their different systems. Few words, because there was a question yesterday about how do we assess biogeochemical variables into our system. So most of the time we use satellite ocean color, and we have to face the reliability of this ocean color product. In many areas, we have to take into account that maybe sometimes we go through optical properties and photoacclimation of the organism, and so what so in terms of imagery, the satellite is not the exact content in terms of phytoplankton, but that allows to evidence most of the chlorophyll blooms, and most of the time compared to models, we have to work on the phasing in terms of comparison. Biogeochemical output are compared also to in-situ data. I just remind you that biogeochemical models have lots of parameters, lots of variables, and most of them are not observed. And we are facing also the sparseness of the data, even if now we have bioargo data that may change bit by bit the way we assess our system. And last but not least, in the way we need to assess the biogeochemical systems, is the fact that we couple systematically the biogeochemical system with a physical system, and what we have learned for the past 15 years is that part of the errors into the biogeochemical solution are due to the physical system. So in the marine service, we decided to start to carefully look at key parameters near the surface, mixed layer depths and so on, that are and vertical movement that are providing nutrients and that may be erroneous and create erroneous blooms into the biogeochemical systems. So this is an example of how do they proceed. Here, from Munir, an example you saw yesterday maybe in the training of comparison between global and regional systems and measuring also the added value of the listed system for biogeochemical components. So I go fast. Something that was asked about satellite ocean color assessment in real time. There are no ways, we have no data for verifying how accurate are the ocean color products from MODIS, MERIS, VIIRS, and so on. So what are doing the guys in Europe when they create these products is to compare to climatology. And for instance, to measure the number of data they have, and this is a PDF, and measuring also how is the PDF compared to the climatology and creating quality index with that. So this is, for instance, a new website provided by the Ocean Color TAC in CMEMS, where you can go and look at the performances every day. Something else that we are working on, just one slide, please take into account that there are other groups in the world that are working on assessment of systems, in particular the Joint Verification Group for forecast prediction. And this group have done a lot of work, a lot of publication for the weather forecast, atmospheric and climate issues. So I think we have a lot to learn from them. So this is what I wanted to mention that. And for instance, in terms of assessing with spatial methods, the biogeochemical parameters. So using these kind of approaches, filtering or displacement approach to better assess some events that we have on the model that have been observed, but not at a good place, not at a good time. So we start in MyOcean to look at that several years ago. For instance, trying to look on the neighboring point, the chlorophyll values in the model and in the satellite data, and creating Garrity scores, for instance. So this is from the UK Met colleagues, trying to, with the foam biogeochemical model, to compare satellite observed value and what was forecast by the system, using this kind of metrics, and contingency table to measure where the model was performant or not. And this is, for instance, when you change the neighboring window in time or in space, and you see that sometimes you get the event, but not at a good place, not at a good time. So it is also interesting to see if the model is able to produce such events. This has been also incorporated into the new framework for the colleagues in the Mediterranean Sea. They are going to do the same. Now something new again from the colleagues in the OGS in Trieste.
Fabrice, please.
Yeah, I'm finishing.
Okay, thank you.
Comparison with bioargo data, biofloats. So this is really new. Please have a look on that. Also at the global scale, comparison to bioargo floats, where we're going to learn lots of things. Conclusion. What I've not discussed with you. Many issues on the representativity about observation and models. The fact that we now have the coexistence of global, regional, coastal operational systems, and I would have time to discuss the benefit of downscaling with many metrics, and the way that we control the boundary and forcing information, or what we need to do to control boundary and forcing information. What I've not discussed with you is the sparseness of observation that are critical in real time, and how to do new things in terms of controlling how the assimilation scheme are performant or not. I had no time to talk about web assessment, which is new in the Marine Service and many areas, and we have done things about that. And I have not discussed about assessment or long-range analysis, but this was partly presented by Keith Haynes last week. Message to bring to home. Partnership is important in evaluation of operational oceanography. You are not expert everywhere. It appears now that ensemble approach reduces uncertainties, and this is important to take into account. We have to learn a lot from other communities, for instance, the atmospheric community. This is really demanding to do what we are doing in real time. We have observations that are not on the best quality. We have few times to proceed. Most of the time, users want the product now. So the time you have to monitor, control, and tell them that the product is bad or good is really short. And we have now to work with users in order to better design our tools to evaluate what they want. To finish, what I want you to bring home is that we need to work with users and understand and provide understandable and reliable information in terms of assessment. Thank you.